Hello everyone, this is Mrs. Lin and welcome back to the third section of electromagnetism. Okay, in this section, we'll be covering when will a current in a wire cause the wire to move. Okay, the wire will move because there is a force. Okay, so in this section, these are the learning outcomes. We'll be covering the first two learning outcomes, and in the later part of the video, for part 4, then we'll be covering the last two parts. Okay, so over here we are supposed to use Fleming's second rule to deduce the directions of forces, field, and current when any of these two quantities are at right angle to each other. Okay, and we should also be able to describe experiment to show that there will be a force that acts on a current carrying conductor or on a beam of charged particles. So when charges move, okay, it forms a current. So it's either a current carrying conductor or a beam of charged particles when placed in a magnetic field. Okay, what happens to the force? There will be a force acting on the wire or on the current carrying conductor. Okay, and what will be the effect of the force if I were to reverse the current and reverse the direction of the magnetic field? Okay, so without further ado, let's move on. So over here, okay, we need to know that whenever there is current flowing through a wire, there is a magnetic field. And when this magnetic field is placed inside another magnetic field, it can be caused by another wire or it can be caused by a magnet. Okay, when the two magnetic field interacts, there is actually a force exerted. Okay, and this force that causes the wire to move or the current carrying conductor to move is actually called the motor effect or the catapult effect. Okay, but we will learn about DC motor in the last part of this, in the next part of this chapter. Okay, so when will a current in a wire cause the wire to move? Okay, so over here I have a current carrying conductor. So the current is going into the paper. So I see the back of the arrow. That's why I see a cross. So I use my right hand grip rule. I get that if the current is flowing into the paper, I point my thumb into the paper or into my screen, I'll get a clockwise direction for the magnetic field. And if I have this magnetic field interacting with the magnetic field of a magnet, so magnetic field of a magnet is always pointing from the north pole to the south pole. Okay, if I have these two interacting with each other, I will to place this current carrying conductor into this magnetic field of the magnets. Okay, in between them, this is what I'm going to get. Okay, I will get an uneven magnetic field. Okay, so on the left side, you will see that the arrows are going up, and on the left side, the arrows are going up. So on the left side, A, okay, I would say that the magnetic field strength is stronger, is being reinforced because both sides are moving upwards. Okay, but on the right hand side, because here is going down, but here is still going up. So on the right hand side, it's actually like cancel away each other effect. So on the right hand side, B side, we will say that it has a weaker magnetic field. And take note that the force will always move from a stronger field to a weaker field. So the force will be moving to the right. Okay, so I have another example over here. So if I were to place them together, you can see over here, this side is reinforced, it becomes very strong, and this side is cancelled away because it's going down, and this is going up, it cancels away, it becomes very weak. So the force will always move from strong to weak. So the force will be moving to the right. Okay, next example. Okay, I'm going to reverse my current. So this current is going into the paper. Now I'm going to have a current that's coming out of the paper. Okay, so you will see that when I interact with the magnetic field, okay, over at the left side now, okay, the magnetic field are cancelling out each other. Okay, and then on the right side, the magnetic field is actually stronger, reinforcing each other. It's going up and going up. So it goes from strong to weak. So if I were to reverse the current, okay, keeping the magnetic field the same, you will see that the force reverse as well. Just now it's going to the right, now the force is going to the left. Okay, so sometimes they will ask you to explain why is it that there will be a force experienced by this current carrying conductor. Why will this wire move, okay? Whenever the wire move, it's because there is a force acting on it. So the larger the force, the larger the movement of the wire. Okay, so sometimes they will ask you to explain in terms of words. So the answer is as follows. Okay, sometimes it will be 2 marks, sometimes it will be 3 marks. So if it's 2 marks, you need to mention that it's due to the interactions of the magnetic field of the current carrying conductor and the magnets. So there's a current carrying conductor with magnetic field, there's a magnet with magnetic fields, and these two magnetic fields interact with each other. And then according to Fleming's left-hand rule, okay, you will produce a force which is perpendicular to both the magnetic field and the current that acts on the wire. Okay, this is for 2 marks. If for 3 marks, you need to state specifically what does each fingers of the Fleming's left-hand rule means. Okay, I'll go in depth into what does each fingers represent later on. Okay, so if it's 3 marks, again, the first part is the same. It's due to interactions of the magnetic field caused by the current carrying conductor and the magnets. Then according to Fleming's left-hand rule, where the index finger points in the direction of magnetic field, and the direction of magnetic field is always from north to south. So you always need to point in the direction from north to south. And the middle finger points in the direction of the current. Okay, the thumb, which is perpendicular to both the magnetic field and the current, will point in the direction of the force. Okay, just take note that for both, whenever you are applying Fleming's left-hand rule, you need to tell me that the force is always perpendicular to the magnetic field and the current. They are all perpendicular to each other. Okay, so let's move on into Fleming's left-hand rule. So Fleming's left-hand rule, it looks like this. So you have a thumb, index finger, and your middle finger. Okay, so how do I remember it? I didn't remember it in this way. Okay, I remember it by father, mother, child. Okay, so like you can think of your father always like to say good. Your mother always point at you to do work. And then the child always likes to point the middle finger. So father is the force. Okay, and then mother is the magnetic field and child is the current. Okay, so just take note that they are always perpendicular to each other. Okay, so you may try to practice on these few questions. Okay, so you have magnets and you have a current carrying conductor in between the magnets. Okay, you are supposed to determine the direction that each of the wires or current carrying conductor will move. Okay, again, I repeat, it moves because there is a force acting on it that causes it to move. So it simply means that they are trying to ask you to find the direction of the force in each case. Okay, so I'm going to go through the answers now. Okay, so in the first case, you'll see that the magnetic field is pointing from the north to south, is going down. So I use my index finger pointing down like this. So I keep my index finger down. I like to always use magnetic field first. It's the easiest, okay? Because current sometimes is a little bit more complicated to see where is the direction of the current flow. So I love to see magnetic field because magnetic field is always going from north to south. Okay, it always points in the direction from north to south. So I keep my magnetic field downwards. Okay, my current is going to the right. So I'm going to put my current to the right. You will see that the thumb is going into the paper or into the screen. So my answer is number 1. Okay, then for the second case, again, I'm going to point my magnetic field first. It's from north to south. So it's going to the right. And then my current is going down. Okay, then you will see that your finger should be pointing at that magnetic field north to south, current going down. You will see that the force is coming out of the paper towards you. Okay, so the answer is actually 2. Next one, over here again, I'm going to use my magnetic field, which is from north to south first, pointing to the right for my index finger. Then over here is my current carrying conductor. I see the tail of it, so it's going into the paper. Okay, so I point my middle finger, my current, into the paper. I will see that my my force is actually down. So you can see magnetic field is left to right, north to south. Current is going into the paper. Okay, my force will be downwards. So this wire will actually move downwards. Okay, so answer is 4. Okay, and then next one. So when you are supposed to draw the forces acting on the wire, please draw on the wire. Don't draw in the air. always students like to draw in the air, out of nowhere, there's an arrow. Okay, the force is acting on the wire, so it must be drawn on the wire. Okay, so now the next example, you can see my fingers over here. I point north to south pole using my index finger, which is my magnetic field. And then my current, I'm seeing the tip of the arrowhead. So my current is flowing out towards me. So you get your force is going actually to the left. Okay, so again, I draw my force directly on the wire. Okay, the current carrying conductor, which is the wire. Okay, then now let's take a look at diagram that's a little bit more 3D. Okay, again, I'm going to point my north pole to south pole for my magnetic field. I'm going to fix it. And then for the current, I hope you will be able to trace the current. Okay, so I'm only interested in the region where I am between, let me go and highlight, where I am between the magnets, which is this region. I am only interested in this region, which is between the two magnets. I don't care about my current in any other areas. So I'm going to trace my current flow. Over here is going up, over here is going to the left, and over here is going to downwards, and here is going back to the right. Okay, I only care about the direction of the current in the yellow highlighted line that I've drawn. Okay, so if you were to use your Fleming's left-hand rule, north pole to south pole for a magnetic field, so my index finger points to the left, and then my current is like flowing out of the paper. This direction is similar to out of the paper. So you get it that based on Fleming's left-hand rule, the thumb, which is the force, actually point downwards. So if I were to draw it, okay, if I were to draw it, I will draw my force on the wire itself, okay, which is like this. Okay, the next example over here, okay, my magnetic field is from north to south. So my force cannot be in B or D, which is parallel to the magnetic force. So B or D is confirmed out. Okay, it's either A or C. Okay, so I point my magnetic field from north to south. My current is going down. You get that the magnetic field is like somehow like going out of the paper. So it's at A. Okay, so over here you can see I have magnets and then I have wire and I pass a small current through it. Okay, and you will see that because of the interactions of magnetic field of this current carrying conductor and the magnetic fields of the magnet, these interactions, and based on Fleming's left-hand rule, there will be a force, and this force is actually to the right. Okay, so what is some of the ways to increase, to make the force larger or to increase the swing of this wire? So I can increase the current to produce a larger swing, or I can increase the strength of the magnet to produce a stronger magnetic field for me, or I can reverse, oh no, if I were to, I want to reverse the direction of swing. Now the swing is moving to the right, okay, or the wire is swinging to the right. If I want to reverse, I want this wire to swing to the left, I could either just reverse one item. I either reverse the direction of the current, or I could reverse the polarity of the magnets. Okay, so I mean, I reverse the poles of the magnets. Either one is fine. But if you reverse both of them, then the wire will continue to swing in the original position. In order for the force to be in the opposite direction, only one item needs to be changed. Okay, so let's watch a video. Okay.
Here, I have a copper wire connected to some batteries. Let's observe what happens when a bar magnet is placed near the horizontal section of the wire. Can you see the movement of the wire? Do you know why this happens? And why it moves in that particular direction? Before we can talk about the phenomenon of the moving wire, we must first understand the concept of electromagnetism. Electromagnetism describes the interaction between electric and magnetic fields. To illustrate this interaction better, we have here a solenoid that has an electric current passing through it. When I place a compass near it, the needle immediately deflects. This is an indication that the electric current produces a magnetic field. On the contrary, when I move a bar magnet inside the solenoid, the galvanometer indicates the presence of an electric current. This means that the changing of magnetic fields produces an electric current. We will apply the concepts that we have just learned to explain how magnetic forces are generated. In this demonstration, I have a copper wire connected to some batteries. Since current is passing through, a magnetic field is also generated around the wire. When I place a bar magnet near the horizontal section of the wire begins to move. This indicates the presence of a force. To understand how this force is generated, let's look at the interaction of magnetic fields from the current carrying conductor and the permanent magnet. In region A, the magnetic fields from the permanent magnet and the electric current are in the same direction. That's why the resultant magnetic field strength in region A is stronger. In region B, the magnetic fields are in opposite directions, so the magnetic fields cancel out each other and the resultant magnetic field strength becomes weaker. A magnetic force will then act from a stronger to weaker magnetic field region. The direction of the resultant magnetic force can also be determined by using Fleming's left-hand rule. When using Fleming's left-hand rule, your index finger represents the direction of the magnetic field. Your middle finger represents the direction of the conventional current, your thumb represents the direction of the resultant magnetic force. Position your fingers as shown. Note that the fingers and thumb are perpendicular to one another. Now that you understand Fleming's left-hand rule, you can use the Fleming's left-hand rule model on your demonstration. With the model, you can now accurately position the direction of the magnetic field and the conventional current. This will help you determine the exact direction of the resultant magnetic force, which is the same result you will get using your fingers. We have just learned that the interaction between the magnetic fields of a current carrying conductor and a permanent magnet produces a force on the conductor. This kicking effect is applied in the working principles of a motor. So the next time you see a motor, think about the interaction between the magnetic fields and how it produces the resultant magnetic force. I will see you in the next video.
Okay, so in the next part, then we will cover about DC motor. Okay, so we move on. Okay, other than a current carrying conductor in a magnetic field, okay, we can also have two current carrying conductor placed near to each other. They will also experience a force because there is magnetic field generated by each current carrying conductor. So this again, there will be interactions of two magnetic field, and again, it will produce a force. Okay, but for current in two current carrying conductor, okay, so we don't use Fleming's left-hand rule. Okay, Fleming's left-hand rule can only be used when there is one magnet and one current. Okay, so you have a index finger for magnetic field and the middle finger for the current. Okay, so it can only be used when there is current and magnets. But for over here, okay, I am using two currents. Okay, so over here, I couldn't use the Fleming's left-hand rule. Okay, so how do I remember that? Ex-students will say, the wires are actually homosexual. Just always remember, the current wires are homosexual. So if they are of opposite direction, that means they are of opposite genders, they actually repel each other. They don't like each other because they are homosexuals. So over here, you can see that the current is coming out of the paper, and over here, the current is going into the paper. So they are flowing in opposite directions. Okay, and they don't like to be with the opposite gender. So these two wires, when they are placed close to one another, they will actually repel. Okay, why do they repel? If you see that I bring these two magnetic fields close to each other, the center portion will be stronger, will be reinforced, because the direction and the center will all be going upwards. The direction of the magnetic field is all going upwards. So in the center portion is being reinforced. So in the center portion is very strong. So again, remember, magnetic field will always go from, or the force will always go from a stronger magnetic field to a weaker magnetic field. So in the center is very strong. Okay, these two wires the force will be towards the right for this and towards the left for this. So these two wires will actually repel like this. Again, remember, the force is drawn on the wire itself. Okay, it's not in the middle of the air. Out of nowhere, there is a force line. Okay, it must be drawn on the wire. Okay, because this in the center is too strong, these two wires will repel each other. Okay, you need to roughly know the magnetic field pattern will look something like this. Okay, so conductors carrying current in opposite directions will always repel each other. They don't like the opposite gender. They will repel each other. Okay, so what happens over here when they are moving in the same direction? So over here, you have a current carrying conductor where the current is going into the paper. You see the arrow tail going into the paper as well. Okay, when they are brought close to each other, you will see that the center part will actually cancel each other out. This is going down, this is going up. So the center portion will cancel each other out. The center portion will actually get very weak. Okay, so the force will actually be pushing it towards the center portion because the side is stronger than the center. So it goes from strong magnetic field to weak magnetic field. So again, the force must be drawn on the wire itself. Okay, so again, remember I say because these two wires are of the same direction, it means that they're the same gender, they love it because they are homosexual. So they will attract each other. Okay, and then magnetic field looks something like that, which is like a peanut shape. Okay, next, you can see, take a look at this example. It says that a strip of aluminum foil is hung over a wooden rod. So a large current is momentarily passed through the aluminum foil in the direction X to Y. Okay, what happens to this aluminum foil? And then you need to explain your answer. So the first step, there's a current flowing X to Y. So these two are like your current carrying conductors. Okay, one side the current is going up, the other side the current is going down. So they are moving in opposite directions. And remember, they are homosexual. They don't like opposites. So when they are flowing in the opposite direction, these two aluminum foil will actually repel each other. Okay, so the diagram will look something like this. Okay, so they will repel each other. And for the explanation, it will be due to they repel each other again due to interactions of the magnetic field caused by the two current carrying aluminum foil in this case. Okay, next we are going to move on into still magnetic field, but now instead of a current carrying conductor, we are going to use the movement of charged particles. Okay, when charged particles move, they actually forms a current. Okay, and you need to know that current is the flow of positive charges. Okay, so the current direction is always the movement of a positive charge. And if the question gives you the movement of a negative charge, current will just always be in the opposite direction to the flow of negative charge, because current always flows from plus to minus of battery, while electrons or negative charge always flows from minus to plus. So current and electrons always flows in opposite direction. But take note, your middle finger, the current must always points in the direction of the movement of a positive charge, not a negative charge. Okay, so let's look into this. Okay, so I have a positive charge moving. So this positive charge moving is going to form a current. So my current is going to move to the right. Okay, and then this cross over here, they already tell you it represents the magnetic field, and cross means I see the backside. So magnetic field is going into the paper. So I am again going to choose magnetic field. I love to use magnetic field as my first finger. So I'm going to point my index finger into the paper or into the screen. And then my current is going to the right. Okay, this pink color arrow is my current is going to the right. It's the movement of a positive charge. Since the positive charge is moving to the right, the current is moving to the right. Okay, so if I were to use my Fleming's left-hand rule, okay, there will be an upwards force acting on this charge. This upwards force will actually cause it to move in a parabolic path upwards. If there is no upwards force, this positive charge will just move straight. But we say that this positive charge will be deflected upwards because there is a force acting on this charge that causes this charge to move upwards. Okay, so you can take a look at this. Okay, so using Fleming's left-hand rule, this is how it looks like. Current going to the right, magnetic field going in, you get a force upwards. Okay, so over here, you can see that if I keep my magnetic field into the paper, still crosses, but if I were to change the direction of the current, so if my current, my positive charge is moving to the right, then my current is moving to the right. But if my negative charge is moving to my right, then my current is actually moving to the left. Okay, current is moving to the left in this case. So if current moves to the left, based on Fleming's left-hand rule, it should be going down. Okay, since this is up, this will be down because I just reverse one thing. I just reverse the current flow or magnetic field. As long as I just reverse one, the force will be opposite. Okay, so you can see the direction of the force is reversed when the charge, the moving charge is changed from positive to negative or vice versa. Okay, and then over here, I'm still using positive charge, so I didn't change the current, but over here I changed the magnetic field. One is going into the paper, one is coming out of the paper. So again, if I just change one item, is either the charge or the magnetic field, the force will be opposite. So in this case, the force is still upwards, as shown just now. But now, because I changed the magnetic field, I reverse it, my force will also be reversed. So now my force will be downwards. And okay, so this is what it means. Okay, you may pause the video now to practice a little bit. Okay, I'm going to go through the answers now. So I have an electron moving up. So it means that my current is moving down. But again, I want to use my magnetic field first. So over here, I see dots. It means that the magnetic field is coming out towards me. I see the arrowhead. So I'm going to point my index finger at myself first. Okay, because it's the magnetic field going out. Okay, then my current is actually going down. Okay, so if you were to use your Fleming's left-hand rule, okay, you will see that the force is actually to the left. So this electron will not move straight up, it will move towards the left. It will form a parabolic path like this. Okay, and then the next case over here, I have magnetic field going into the paper. So I'm going to point my index finger into the paper as shown. Okay, my current is going to the left. Okay, because this is the movement of positive charge. Okay, based on Fleming's left-hand rule, you will get that the force is downwards. So this charge will be moving downwards in a parabolic path. Okay, so the next example over here, determine the direction that the copper rod will move. So I have a magnetic field. Okay, so this magnetic field is going into the paper because I see the arrowhead. Okay, then next I need to know where's my current. So my current is supplied by the power supply. So my current is going up and then going through these aluminum rods and then going down over here and then going back to my battery. Okay, so which arrow do I need to take a look for my current? Remember, I always want to take a look at the one that is interacting with my magnetic field or the one that will move in this case. Okay, because I will have a force acting on it, I have a magnetic field, I have a current, I will have a force acting on it, and to determine this force, I need to use Fleming's left-hand rule. This force is the one that caused this copper rod to move. So the copper rod could move left, right, up, down, into or out of paper. So let's come and do. Okay, so I'm only interested in the movement of the copper rod, which means I am only interested in the current over here. So I'm going to highlight pink color. Okay, this is the part that I am interested in because my force can only move this. I couldn't move the aluminum rods because the aluminum rods is already fixed with the power supply. Okay, so I don't care about my arrows to the right or to the left. Okay, I only care about this arrow going down. So if I were to apply my Fleming's left-hand rule, magnetic field going into the paper, current is going down, I will get my thumb pointing to the right. So this copper rod will actually point to the right, will actually move to the right. Okay, so over here you can see my Fleming's left-hand rule. Okay, current is going down, magnetic field is going to the right. Okay, so I get a magnetic field going into the paper, sorry. So I get my force going to the right. Okay, so let's do a very, very quick recap of some sentence. You need to tell me, are these sentences true or false? Okay, so the first one, let's go through. A current carrying wire held parallel to a magnetic field will experience a force. Okay, the answer is false. Okay, because it is held parallel. Okay, in order to experience a force, the current carrying conductor must be perpendicular to the magnetic field. Then I will produce a perpendicular force again. Okay, next question. Reversing the current will actually reverse the direction of the force. This is true. Okay, as soon as I reverse current or magnetic field, I will reverse the force. Reversing the magnetic field has no effect on the direction. No, it has an effect. I could have reverse current. This is one of the options, or reverse magnetic field. Only these two options to reverse the force. So this one does have an effect. So it's false. You will only need to know the direction of the current to predict the direction of the force. This is false. I need current plus magnetic field. I need two things in order to determine the force. current, and magnetic field. That's why it's the father, mother, child, three fingers. Okay, increasing the strength of the magnet or the current will increase the size of the force. This is true. Or increasing the length of the wire. Oh, this one is not in your syllabus, so I will skip this. Okay, so a summary of what we have covered so far. We have covered that there will be a force acting on a current carrying conductor when it's placed in a magnetic field. There will also be a force acting on a beam of charged particles, not current carrying conductor, but a beam of charged particles when it's placed in a magnetic field. Okay, so just take note for both sides. Okay, the factors that affects it is very similar. For current carrying conductor, you can increase the force by increasing the current. Okay, for here, you can increase the force by increasing the number of charges or the charge on the particles. Okay, next one, the force can be increased when the strength of the magnetic field increase. The same. Okay, over here, I must also be placed in a magnetic field. I want a greater force. I need to have a greater magnetic field. Okay, and then this is also the same. The force acts in the opposite direction when the current is reversed. And the force will also act in the opposite direction if only the magnetic field is reversed as well. Okay, so forces act in the opposite direction when the polarity of the magnet is reversed. Oh, so this is what I just said. Okay, so I can either reverse the magnets or I can reverse the current. Either one of them will reverse the force experienced on the wire or on the beam. Okay, that's it for this part of the video.